Okay, so I wanted to find fiber bundles. So what's a fiber bundle? So I think I have another video on this, but so this was the first thing. Okay. So fiber bundles are things that are maps which locally look like a fiber. So let me give some examples first, right? So let's do an example. We'll do a bunch of examples. Okay. So if I have, okay, so let's define PNC. Okay. So this is going to be a topological space. It's going to be the complex numbers, and then I'm going to remove 0, the origin, and then I'm going to take an equivalence relation. Okay. And the equivalence relation is that, so if I take a bunch of numbers, so z0 up to zn, so this is going to be equivalent to, well, lambda z0, lambda zn, for lambda, so this is for lambda, a non-zero complex number. Okay, so in particular, okay, so this is what we have. So this turns out to be a certain topological space called a manifold, since it's locally Euclidean. But there's a map from here to here, right? So there's a map here. There's a map here from, let's say, Cn plus 1. Okay, modulo, so this is this thing here, to this complex projective space. Okay, and then if I were to take a point here, right, what does the preimage look like? So the preimage is going to look like a bunch of points, right? So so this thing here, so it's going to be everything that's equivalent to this given vector, right? So what we're going to have is we're going to have a bunch of copies of. So it's going to be, okay. So what do we have? So it looks like a copy of C star in here. Okay, and this is just an abbreviation for, this is what the fiber looks like. So if I call this map P, right, and I take a point, so there's a notation that goes along with this. So the equivalence classes, right, are going to be denoted like so. Right, so these are all not all 0, and then in here, so the inverse image of P0, so P inverse of this thing, this class, well, it's just actually going to be the whole set of all these things. So this is going to be lambda z0, lambda zn, so for lambda in C star. And actually, any two elements differ by a single lambda, right? So this thing here is actually homeomorphic to C cross, right? And the map, say, could be given by, fix your favorite element, right? And then so what would a map be? So a map from P inverse, say, of Z0 to Zn would be, so if I took an element here, W0 to W0 to Wn, okay? So this would be the unique, so we go like this, and this is a map here, and it depends on, say, Z0 to Zn, okay? And it goes to lambda, and this is the unique element where, W0 Wn is equal to lambda Z0 lambda Zn. So I guess you could just divide two of the coefficients. Okay, so this is a fiber bundle with fiber isomorphic to the punctured plane. All right, so that's one of our fiber bundles. There's another bundle that you could do. You could kind of fill this in, right? And you could get another bundle where you do Cn plus 1, right? C. And in the fibers here would be the vector space spanned by one of these guys. So then if we did this, I don't know, we call this Q or something, right? This goes into this space as well, right? So the fibers, so in this case, Q inverse of a point. So this is the vector space, so the C vector space. The vector subspace of Cn plus 1 spanned by any one of these elements. So this has a special name, this one. This one's called the tautological bundle. Okay, so, all right, so what's another example? Okay, so to do another example, so we need a certain fact. A fact. Okay, so that S1 is homeomorphic to P1 of C. By the way, let me just say a kind of remark here. You can do the same thing with R, right? So there's these other spaces that are Pn of R. Makes sense. And then there's some notations that people use. So I'm calling this Pn of C. So some people call this CPn. And some people call this one Pn of R, RPn. Okay, so these are just different notations for the same thing. A real projective space, and then complex projective space. And okay, and so this is the kind of the Riemann sphere. So this is, we think of both of these as C union infinity, right? Where where we have the point infinity is really the point. So how do we get the point C? Right. So when Z is not 0, let's say Z1 is not equal to 0, right? Then we get some Z0 over Z1, and this is an element of the complex numbers. So this is a map. Okay, so this is a map from the subspace where Z is not equal to 0 into the complex numbers, right? But when Z1 is equal to 0, there's a special point, right? And that's this point. And so we kind of treat this is sometimes called the real projective line, and this is where we adjoin a point at infinity. Okay, and so there's kind of, this is S2 here, the Riemann sphere. Okay, all right. So now I can kind of explain another fibration. Let's do another fibration called the Hopf fibration. Okay, so let's do another example. These are Hopf. Okay, so here what we'll do is we'll look at a map S3 to S2, but we'll view S2 as P1. Okay, P1 of C. Okay, and so here we're viewing this as the set of complex numbers Z1, Z2 in C2, such that, well, Z1 squared plus Z2 squared is 1. And then, I don't know what we want to call this map, maybe H for Hopf. So then H of, and we'll define H of Z1, Z2. So this will be, we'll take Z1, Z2. Okay, so there's a unique representative for each one of these things by normalizing them to have norm squared equal to 1. Okay, so so this is the map here, and so you'll notice that if we given two elements on the 3 sphere viewed as inside the complex C2, right? So we see that for Z1 and Z2 in here, in S3, right? So this thing is similar to, and so this is just using the equivalence relation that we defined previously, up to this equivalence relation that we used to define projective space. This is equivalent to e to the I theta Z1, e to the I theta Z2. Okay, so this is another point in S3. Okay, and in particular, H inverse of some point here, Z1, Z2, well, this looks like a circle, right? It's the set of, well, e to the I theta Z1, e to the I theta Z2, well, where theta goes in between 0 and 2 pi. Okay, so the idea here is that we kind of have so we have our maybe I'll draw it here. Okay, so here's P1 of C, right, which we're viewing as the sphere. And then S3, something like this. So this is S3 is really, R3 union infinity. So that's kind of what I'm drawing here. And then if I take the preimage of a point on P1 of C, right? So this is maybe the complex plane union infinity, I get a circle, right? So there's like a whole circle's worth of stuff. And so this is what's called a circle bundle. So this is a circle or U1 bundle. Okay, so U1, we call it a U1 bundle because, so let's recall that here UN, so this is the n by n matrices in complex numbers. So this is the A in C to the n by n, such that A star is equal to A inverse. And this is the conjugate transpose, right? So this is A bar transpose. Okay? So this is the unitary group. So it's a topological space and a group, and the multiplication is continuous. So U1, right, is really the set of e to the I thetas, for theta in 0 to 2 pi, right? So this is really, these things. So in the complex plane, it looks like this, right? E to the I theta is here. And, and it is a topological space. It's just isomorphic to S1, as a topological space. All right. So and so this thing here is a circle bundle, and the fibers are circles. So this is what we have here. Okay. So what's another example? So let me say that there's kind of like generalizations of this that may be useful. Right. So there's maps like S3 to S7 to S4, right? And I guess the idea is to view this as like P4 in the quaternions in some sense, and then this thing is the so this is the Hamilton's quaternions. Right, and there's S7, S15 to S8, right? And so this uses the octonions, right? And I guess the construction of the projective space in the octonionic case is it doesn't exist. I guess maybe for 2 it does or something, but yeah. So maybe this needs to be a P2. Okay. So what else do I want to say about this? I don't think we need to say much more than this. Okay. So so these are other. So this is an S3 bundle. This is an S7 bundle. And it turns out that the spheres that you can equip with group laws are these. All right. So those are the ones that can be made into topological groups. All right. So what's another type of bundle? So here's another example. Okay. So we can take the sphere. Okay. It's the tangent bundle of the sphere. Okay. So here's the sphere S2. Then I can look at all these vectors that are inside of this, that are tangent to this point. Okay, so this is the tangent bundle of the sphere, so what I've drawn here. So we're looking at what's called TS2, or some people call it TS2. So this is the tangent bundle of the sphere. Of the two sphere. All right, this thing here is the set of, well, XV in, all right, so in S2 cross R3 such that, well, X dotted with V is 0. So we're looking for, so we kind of have some vector here, so like this, but we're going to view it out here. And then we look at all things in the plane, like so. Okay? So in particular, there's a map there's a map induced by the projection map here. So there's a map from TS2 to S2, right? And then we could take a point X naught here. And then in here, there is a collection of vectors, X naught V, when these are the vectors that are just orthogonal to X naught. Okay? And so there's a whole plane's worth of them. There's a whole plane's worth of them. Yeah. So fibers are isomorphic to R2. To R2. Okay? So this is what's called a two-dimensional real vector bundle. So a vector bundle of real rank 2. So this is a vector bundle of real rank 2. Or maybe a real vector bundle of rank 2. Why is it called a vector bundle? Well, you can actually equip this with a group, each of the fibers here, with a group law. And yeah, so that's a thing that you can do. Okay? And so it's like a vector space at each point, right? And so, yeah, that's one of the things that we are interested in. So, yeah. Okay, so what else are we interested in? So there of course there's the trivial bundle, right? Trivial bundles. So maybe we draw them like this. So this is X, and then we could just draw Rn here. So X cross Rn, P. So this is a trivial. This is the trivial Rn bundle. Okay, so that one's silly. This one is not trivial, right? And one of the things that one of the big theorems about this is that, so one of the things that we're interested in is we're interested in, so one of the, a great pastime for mathematicians is, okay, so if I'm given, so this thing can be defined in total generality here, this tangent bundle thing. But if I'm given T of X and X, right, so one of the things, if I call this P, one of the things I want to know is how many sections, so, does this thing admit global sections which are say non-zero in the sense of this vector space structure, So at each point there's a 0 vector, and you want to know, so one question is, so do there exist global sections which are nowhere 0? So, yeah, and so here, if we write this, so suppose that x is embedded into Rn for some n, right? Then that we could do the same thing. So what is it? What is a section? So a section is so what's a section? So here we want this map and this map to be composed to get the identity. So we want S composed with P to be the identity on X. Okay, and so this thing is what we consider to be a vector field because if I draw the sphere case again, and so what do we? So let me explain what I mean by nowhere 0. So we have S of X, right? And if it's embedded, right, then this thing looks like a subspace of X cross Rn, right? And then this looks like X, so it looks like X, and then we have some V of X, like, so that's some vector that we're choosing. And so this is in X cross Rn. And, then we can add those and multiply those and whatever. So what do I want to say? So this is, I'm not going to make a set of these. So this is what this is. And so we want nowhere 0 means that for all x in X, V of X is not equal to the 0 vector. Okay? And this leads to this thing called the Hairy-Ball theorem, right? The answer for S2 is no. Okay, so this is a no on S2. Okay. So we have these bundles. So let's do. So let's do another example. Okay. So one thing that we could do is we could say there's a map from S1 to P2 of R. Okay, just like we projected them. And so this one here is, so we have S1 as a circle. And then what does this thing do? So this identifies things on the circle that are multiples of each other. So this thing is like a circle, but like where the 2 points, so here, these 2 points become identified, right? So this thing gets wrapped around. Okay, so this is, yeah, so this is, I don't know what we want to say. This is like the, okay, so if I take a single point here, it gets mapped into 2 points here, right? So this thing has finite fibers. So this map here, this has finite fibers. And so this is an example of what's called a covering map. So a covering map is a fiber bundle with finite fibers. Right, so a finite set. Okay, what's another example of a covering map? So what's another example of a covering map? So here we can take the circle, and then we can kind of unwind the circle. This is R. Okay, so this maps to here, and then if I take a point, it'll have, tons and tons of preimages. It'll have countably many preimages, but the fibers are still discrete, right? So this is still a covering map, right? It's just a set with the discrete topology. So and here we can view this as, say, R mod Z. Okay, so this is homeomorphic to this. Okay, and so yeah, so here are the fibers in this case are a countable set with the discrete topology. Okay, so what's a fiber bundle? Okay, so now let me give a definition. So a fiber bundle with fiber F and F is a topological space, is a map P from E to B such that there exists a cover. So of B, so let's say of UIs for I and I, so some index set of B, and so let's draw it like this. Here's E, here's B, right, and then there's UI, and then we have this thing. So we have P inverse of UI, and then isomorphisms UI cross F, right, and isomorphisms. So let's call this phi from P inverse UI to UI cross. So homeomorphisms, right, in the category of topological spaces. And isomorphisms like this. Okay, so this is sometimes called fitting in this way. So this is sometimes called these maps here are called trivializations. Right, and if we're given to, so one, an alternative way to define this, we could have said something like for all B and B, there exists a U subset of B open with, B and U and a trivialization. Some trivialization. We could call this phi of U from P inverse of U to U cross F, right? So I didn't really have to fix a cover to do this. I could have just said for every point locally it looks this way. One small remark is I want to be able to use this terminology while we're here. So let me just cover these terminology bits. Okay, so what's a covering? So this is a fiber bundle with fiber F and a fiber bundle with fiber F and with fiber F with the discrete topology. Okay, so here we have this, and then this is given the product topology. And so what does that mean? So that means like over an open set U, right? If we have a finite set, so this is U, and this would be P inverse of U, it would be like this. So, what I'm saying here is that, if S is a finite set, say like 0, 1, 2, right? S cross U, and this is with the discrete topology, right? So this is the same thing as U disjoint union U disjoint union U. Okay. So that's one way to think about products with the discrete topology. What else do I want to say? We have fiber bundles. We have this. Okay, so maybe the last thing, and I don't think I'll use this, but I'll say it just for sake. So sometimes we, like on vector bundles, we like to impose extra conditions. So there's this condition on transition maps. Okay. So if we're given two trivializations, right? So suppose we have, let's do here, E. Okay, we have P. Here's the base. Okay, we have U here. We have V here, right? And we could take P inverse of U, and this could be isomorphic to U cross F. And then we could have P inverse of V. And so this is isomorphic to V cross F, right? So this is, say, by psi V, and this is, or sorry, phi V, and this is phi U, right? One thing that we could do is on P inverse of U cross V, right? Or U intersect V, like this. So, right, there's this isomorphism here. These are equal, I guess. There's this isomorphism here, which is induced by phi U. And this is U intersect V cross F. And then there's this isomorphism here, phi U. And this is U intersect V cross F. Right? And then there's a map from here to here. Right? So if I go like this, so if I do phi inverse U composed with phi, so this is what's called the transition map. From these two trivializations. So, okay. And so often we impose conditions on these transition maps. So often impose conditions on trivializations. Oh, I had another great example of how this could get more complicated. Okay. So, but let me just say what an example would be, right? If F is Rn, right? Then asking transitions to be linear. So these to be linear. Or there exists a collection of linear maps, right? So means that it means that this map here, this is a vector bundle. Okay. So that's actually the definition of what a vector bundle is. And let me say that this comes with part of this is part of the data, right? So it's the collection of trivializations of this form where they're all compatible in this way, right? So it's not like every transition map you get is that. So maybe that's the best way to do that is in terms of this type. So we could have defined a vector bundle with a cover with specific trivializations such that this thing holds, right? And that's a vector bundle. But if we do it, yeah, that's all I'll say. That's all.